हाँ लोकेश ज्वाइन नहीं करो।
सर अभी
हाँ 1 बजे है ना।
ठीक है सर
फिर
करता हूँ।
ठीक है, तुम 10-15 मिनट में करोगे तो कोई प्रॉब्लम नहीं है।
सर
स्क्रीनशॉट वैसे भी 10-15 मिनट के बाद ही होंगे। मैं ना तुमको एक पीपीटी भेज रहा हूँ और
सर
एक एक्सेल फाइल भेज रहा हूँ। पीपीटी में सर्टिफिकेट है, एक्सेल में नाम और वो है। तो मिस्टर डॉक्टर वगैरह जो है वो ठीक करना है, नाम कॉपी पेस्ट करना है और इंस्टीट्यूट का नाम पेस्ट करना है। तो करीब 37 है अभी। 38 वाला जो है वो मैं भेजता हूँ फिर बाद में एक, या मैं कर लूंगा खैर, ठीक है। तो तुम इतने करके मेरे को कब तक कर सकते हो?
सर कल भेजेंगे सर आज कल।
कल सुबह भेजूंगा।
हाँ सर कल सुबह।
और वैलिडिटी में रहूंगा ना?
हाँ सर।
जहांगीर, हेलो।
Yes, Altaf.
We'll start in 2 minutes. If people don't join still, we'll just start it off. They do start by 10-15 minutes, so better we'll start.
Start now?
No, in 1 or 2 minutes we'll start, as per your
Okay.
convenience.
Okay, I'll just wait another 2 minutes, then I'll start. Hi Altaf. I'm going to start now. Is that fine?
Yes, that's fine.
You can see my screen, right?
Yes.
Okay, thank you. And again, welcome everyone in my last lecture. So yesterday we started microgrid, and so far, we discuss like microgrid definition, why we need microgrid, and what are the advantages and challenges if you compare with the main grid. Then we also talk about different microgrid control scheme, and then we also talk about how we can identify ice landing condition. Then I talk about microgrid stability. So today what I'm going to do, there are only few slides on stability. I'll just go quickly on that because again this is more like mathematics. And then I will show you mainly that, like, what are the design step that you need to follow if you are going to design a new microgrid. Yeah. The design process are almost quite same, but based on your like use cases, maybe your objective function would be different. And then if time permits, I'll briefly talk about few other new technology that is being used in smart grid. So okay, let's start. So another important parameter, if you would like to do that small signal stability analysis, it is called participation factor or participation matrix, and this is actually quite important because that will give you insight that when in your system you have got like hundreds of devices, which devices are contributing most to make the system unstable. And sometimes it might be not a single device, it could be more than one device, but that will give you idea. For example, let's see if you have got 100 synchronous generator, then it will give you idea that which generator I should give first priority. If you would like to design a new controller, and this participation factor, that will give you that idea that which generator or which devices is contributing in the most critical modes. And again, this is nothing but just like left and right eigenvector. And again, even in MATLAB, there is a very simple way. You can just determine this participation factor. And other factor is called residue. Residue is just like when you are gonna design the control, there might be a number of output signal you can have. For example, you can have output speed for a machine, you can have output voltage, you can have current, power, and so on. Now, which one actually you need to use as a feedback signal that will give you best control performance, and that is being actually calculated by using the residue. And here residue is again nothing but it's just like your output matrix, input matrix, and then other two like eigenvector that's coming in your matrix. So this is also you can easily calculate in MATLAB. Now here I'm just showing like one example. Here, for example, let's say you have got like 3 microgrid. Here, this is microgrid 1. This is like microgrid 2, and this is microgrid 3. So these are the three different microgrids. So what we have done, initially we calculated eigenvalue for microgrid 1, then we connected microgrid 2, I mean without having any coordination, and then we connected microgrid 3 without any coordination, and this, like, we just connected using a small DC link, and then we analyze its stability. Now again, I mean, this is like, could be like, your two, like here, a DC with an inverter. That's the way, I mean, you can represent by a equivalent circuit, where you have got like a load, you have line, and then you have got a DC with, like, its filter, inductance, and resistance. And this is connected with, another devices. Now, this is again, I mean, I already mentioned that's the way, I mean, we can represent a photovoltaic system. So you have got your PV, and then your DC link, your inverter, and then you have got, line, which is connected with the main grid. And same for, like, wind turbine. As I already mentioned, this is like a fourth generation wind turbine. So it is connected, like, 100% connected through the inverter converter to the grid. So we mathematically, presented all of these, like, devices. And then again, I mean, we calculated that, small signal model, like we calculate all the matrices, and here X, like, state vector, which have got, like, 25 state vectors. So that means here we have the system that 3 microgrid have, it actually have 25 states. So the matrix that you will be getting, like 25 by 25 matrix. And then after doing that, we just calculate eigenvalue. And here, I mean, I'm not showing all the eigenvalue, but the eigenvalue which is more critical, like closest to the imaginary axis. So here you can see, like, initially it's like a microgrid 3, then we added microgrid 1 and 3, and then microgrid 1, 2, 3. And you see, like, microgrid 1 and 3, it's actually pushing that eigenvalue to the imaginary axis. So that means if we don't coordinate, if we just, interconnected like more than one microgrid, then it can actually reduce that stability margin. So that's why, I mean, if you would like to have multiple microgrid, I already mentioned that we need better control, optimization, and energy management, so that when we are interconnected, it does not have any negative impact on the overall performance of the microgrid. Okay, that's like that stability analysis technique, as well as some example. So next, let's talk about, like, if you want to design a microgrid, like, what are the requirement, what are the process that you need to follow. So here, so the first requirement, that's you have to define the microgrid boundary. And I already mentioned previously that microgrid could have defined boundary. And here's some of the example as that. Is it like for a individual customer? Is it for a university campus? Is it for a whole substation? Or it is for like a circuit means it's like a complete certain area. So after defining the microgrid, so the next thing, you have to find your missing load as well as generation, because that is quite important. And to do that, what we have to do, we have to collect the data for the load consumption in a particular area for which you would like to design the microgrid. For example, if you have a university campus, in your campus, you have to find out what are the different loads in your campus. You also need to find out like their energy consumption. And also it is not only in a particular time of the day, it has to be at least like it's better if you have got like 2-3 years historical data. So that will give you like idea the power consumption like in different season, weekdays, weekend, and sometimes like now during the COVID, before and after the COVID. So that will give you better understanding about that load pattern or energy consumption pattern in that particular area. And based on that, next, you can also, do some initial techno-economic analysis just to find out what sort of mix of generation, might be optimal for your particular system in terms of the cost as well as technology readiness. So while you are doing things, you have to also define what sort of reliability you need for that particular microgrid. If you want higher reliability, then your cost would be higher, because in that case, probably you need to have some additional generation capacity. You need to have better protection control inside your microgrid. And these are the some of the index that we generally use while we define reliability. And if you someone work in the power system, you might not like SIDE is SIFI. This is nothing but like your average energy interruption index, duration, and then like yearly energy outage frequency, like for example, like as a customer for the whole year, what what's the duration, like it could be in terms of the minute or hour. What is the duration, your that particular area was without power, or the frequency, how frequently the interruption is happening in that particular area, and what was the minimum value that you want. And even like when myself and Ibrahim was talking about PV and battery sizing, that we say that you want that interruption value very minimum, like it's like 0.01 or 0.001%. So here also, you need to define what sort of reliability requirement you need for that particular microgrid that you would like to design. And then this transition, like from grid connected to islanded to grid connected, what sort of transition you need, how long you want them to restore power in your island. And also it's a good idea to define different types of load, like what are the critical loads, what are the non-critical roles. Would you also include demand response in your design, and what are the peak loads? Because if you want demand response and without demand response, definitely, I mean, your design would be different. And if you'd like to operate in isolated during that extreme weather event, like, I mean, how long you would like to run during that isolating period. And also, I mean, in terms of generation, I mean, what sort of requirement you have? Do you want renewables? Do you want, like, renewables or mix of renewable plus fossil fuel? And then what sort of energy storage you need? So these are all of the things, I mean, you need to think critically before you know you are going to design your microgrid. And this is the like flow diagram, like that is, I mean, for your design requirement that I mentioned, like for example, initially what you will do initially, you will just select your site, and as I said, this is could be your campus, this is could be a community, or this is could be a couple of house, or could be a single house. Then you need to collect the data for that particular system, a particular area. And what sort of data, I mean, you need, I'll just explain in details in, I mean, in coming slide. Then, I mean, the next step would be like, you will identify your design objective and what are the design basis threat you have in that particular area. Is that particular area frequently experience flood or tornado or bushfire? So those are the things also, I mean, you need to consider in your model. And then you need to have, I mean, electrical drawing for the area, I mean, that you would like to design the microgrid. You also need to characterize your renewable energy resources. For example, if you have a PV, I mean, you need to do some modeling just to see, like, considering that local radiation and as well as also temperature. I mean, for a certain PV system, what sort of power you will get for like a day, for a month, or even yearly. And as you this microgrid, as definitely I would like to make the system smarter. You also need to think about your communication and information network facilities that you would like to use, and what are the currently available, or what you might need on top of what is already available. So this is more like the data gathering and stakeholder coordination phase. So the next, I mean, you will go for your conceptual design and conceptual preliminary design. So you can do initially your design screening model. Like initially, you could have like multiple option. So you just screen like what are the possible design option you could have based on your all the resources that I mentioned previously. And then you'll draw a have an initial network model. And once you have that initial network model, you will do some performance and reliability analysis. And from that, you will develop your initial design option and performance requirement. And here option is not a single, it could have multiple option. Next, I mean, you will find out what are the components and network. What are the component you need. Also, you will do some network design analysis. And then you'll find out like, what sort of control, protection, or even like, if you need like cyber security requirement. And then you will find out your design. And then if it is adequate design, if not, then you'll come back, do some optimization, and that's how probably you will find your preliminary design. Does it make sense, or you have got any question or comments for the like a preliminary design? Is it clear or does it make sense? Or
Sense, sir.
Clear, sir.
Okay, thank you. So in that case, I'm not going to repeat, but if it is not clear, I can repeat again. So next, you need to know what are the main actors in the microgrid. And here, so the main actor of the microgrid scenario who occurs multiple times in your different use cases. And I'll mention like, what are the use cases for microgrid in coming slide. But the actors, we mentioned here, we can classify into people and organization, and then system and device, because those are the things, that are involved in the microgrid. So there will be some people, there will be some organization, and then system and device in the microgrid. So if you think about people and organization, one of the things that who is the microgrid operator? That's a very important thing. You need to find out. And the microgrid operator, that is a organization, and it's responsible for like operation of the whole microgrid, and also contracting with prosumer inside and outside the microgrid. Then overlay grid operator. So what the grid operator in which microgrid will have a connection point. So this is the point of common coupling, and you might interconnect your grid microgrid with that grid. So that also another entity. You need to know, and also you need to contact with them as well. Then prosumer, that is like, it could be like a person, or it could be an organization. Sometimes it could have like a community type, like a group of people who might own a single battery energy storage system. So that's why it's like, it could be the consumer, or it could be a DER owner, or it could be the storage owner. And then the service provider, because again, that also could be a person or organization who provide different kinds of service to the microgrid operator, just to make sure that that microgrid runs well, after you install the microgrid. So there should be some person who look after that microgrid, which is like a service provider. So this is all like people and organization. And then, as I said, like, you need also have prosumer, and that's I mentioned, like, they are either DER owner, consumer, or storage owner, and they have got their own like, responsibility. So if it is DAR owner, they will operate a DAR which is connected to the microgrid, right? A consumer which might be like a private business building, or even large industrial building, or a transportation like a EV charger, who will utilize electricity in that particular microgrid. And storage owner will store energy, and then it can deliver energy when there is a need. And microgrid operator, again, this could be a retailer, it could be aggregator, or it could be like a system operator. That is also very important, and you need to find out who will actually, operate the microgrid. So it's not only design, but also like, is it like, operated by the grid operator, or it is operated by some group of people, like it could be some aggregator, or even it could be a retailer. So that also, we need to find it out. And based on that, we'll have our different business model. And these are the system and control, and probably, we already talk about all of them: microgrid control, DR, storage, home energy management system, and it could be having some smart devices, sensors like sensor, circuit breaker, switch, and so on. Now, those are the entity of people are involved with the microgrid, and it is important that you also need to clarify those things while you are designing and planning for a microgrid. Now, as I say, when you microgrid, you design or install microgrid, there could be different use cases. So is it something like that you are designing a microgrid? Is it something like selling and buying energy to the external market? So it could be like just like for a business purpose, or you could just sell power just for the balancing demand, or sometimes it could be that you would, your microgrid would like to provide energy ancillary services for the other grid, or it could be that it's just like we are having microgrid to give like main priority is just supplying power during the isolated mode. Or it could be that you are just having like a open trading and communication platform for all internal external trading. So those are some of the business use cases that could be like um, that could be some objective when you are designing the microgrid. It could be other like controller management use cases as well. So it could be that you're just doing like to ensure stable operations by just balancing supply and demand on different time scale. Or you could do it to provide demand side management, or supply side management, or storage management, or it could be that for block start in the isolated mode. So these are also could be some of that use cases that you can think about when you are doing or when you are designing the microgrid. Now, while you are designing the microgrid, the first step, you need to do that economic feasibility study, because at the end, whatever doing, it might be very resilient. It might be very technically sound, but at the end, if it is not economically feasible or profitable, nobody will invest, right? So that's why once you have got that pre-feasibility design, then so the next thing you have to do your techno-economic analysis. Here techno-economic analysis is mainly like while you have got all the data that you need to design for your microgrid. For example, your load input data, your generation input data, and then you could your storage. All the components that I already mentioned, and then you need to do some economic study just to show like what could be the total spending that you need to do for designing your microgrid. So this is not only also like an upfront cost, but also at the same time your maintenance, replacement, and those sort of costs that you will do. Mainly probably you'll find out, let's say for next 10 years, what would be your capex, opex, everything. And on top of that, you also find out like what, I mean, benefit that you can get. And here benefits mean mainly the first one is like economic benefit. But sometimes also like, it's not only economic benefit, but it could be like, other environment, social benefit as well. So you'll determine what sort of benefit actually you are getting from that microgrid in the next 10 years. And then, I mean, you'll compare like, how long it will need to get your return for your investment. And that's how you'll find out whether, I mean, this is feasible, why, like, it is like, that profitable, I mean, when you're doing that investment. And if it is says like yes, then I mean, probably you'll go for next, like, for your other, study. Next also, I mean, you have to do technical study as well. So as I mentioned, what sort of data you need. And here I'm just giving like, some of the example that you need while you're thinking for, I mean, designing microgrid. For example, what sort of participant we have got, I mean, what percentage residential, what percentage commercial, do you have any farm, like, it could be agriculture or it could be, other farm. And then you need that information for all of your NMI, feeder location, and those sort of things. And then it's the network information, the load data, meteorological data. And in that particular data, is there like any existing like renewable energy sources? If yes, what's their location, what's their size, and do they have got like, any regulator in the existing system? So those sort of things, I mean, you need to find out. So as I say, like, so the more data you have, so the better design you will be able to do it. Because it's not only like the current demand, but also you need to forecast what could be the, like, next 10, 20, 30, 40 years. Because the system that you are designing is not for like, 1 year, 2 years. So you need to also do some forecasting what coming in the next 30, 40 years. And to do that, I mean, we need some historical data. But sometimes, I mean, it can happen that, the area that you are doing, there is no data. So what you can do? So in that case, is probably, again, you have to start from a very rough figure, just by estimating, like, what sort of number of appliances that might be in that particular area. And here I'm just showing, I mean, and in that case, I mean, you need to find out what sort of appliances there, what's their rating, how long, they will be on. So here I'm just giving like some example and some rating. For example, if you have a light bulb, is it like, 100-watt bulbs, for how long it will be used? So here it could be like a 10 hours per day. Then you're just finding what's the corresponding energy. Simple like your electric oven, your, pot, your toaster, microwave, and another one is this electric oven, which is like, convection. And then it could be you have a refrigerator, and there could be, I mean, different type of refrigerator as well, and each one have got their individual rating. Do you have any, like, desktop computer, and then laptop? And if you have a desktop computer also, like, how long it will, like, you will actively use, or how long it might be in sleep mode? Because in two different cases, I mean, it will consume two different types of power. And also here I'm just showing, like, some other devices that might have in your area, I mean, in your microgrids, for example, television, fan, phone charger, washing machine, LCD monitors. So once you have got all the ratings and how long, it might be on, that will also give you some rough estimate that energy you need for that particular area. And this is also given like, rough percentage. So that a load that you might have. So for example, the cooking, it could be 4%, lighting 7%, freeze and freezers 7%, other appliances 16%, heating and cooling, because that's one of the major load, 38%, water heating, that is also another major load, 25%. And the standby power, that could be like 3%. Yeah, so that give you like, as I say, like some rough estimate that you could have like in your microgrid demand. The next thing, I mean, as I say, like you also need to identify what sort of design basic thread you might have in that particular area you are going to design the microgrid. Because based on the thread, your impact could be different types in terms of cost, in terms of the duration of the events, and then I mean you can analyze and define those events, like while you're designing the microgrid. And here I mean some of the events, as I say, like it could be some natural disaster like hurricane, flash, tornado, earthquake. You could have some unplanned event like local and regional service interruption due to some equipment failure, some malfunction of the equipment, or could be some human error. You could also have some intentional or mail event, for example, cyber attack, physical attack. So these are also other things I mean you need to consider while you are going to design your microgrid. And I already mentioned, like in the designing screening model. So as I said, when you're doing screening, you have got like several option, and from that screening, before doing any detailed analysis, just from your experience, you'll just narrow down your design option, considering like different investment key relationship, like between load, PV, diesel generation, and so on. And then you could also have electric network model, as I mentioned, just to ensure voltage magnitude remain close to that your rated value, and also it does not exceed any either feeder capacity or transformer capacity. And then I mean later also you'll do some performance assessment and optimization. You could also like divide load in terms of the criticality. And here in most of the cases we have got three categories, like tier C, tier P, and tier O. Tier O, that is not that important to the performance objective during microgrid operation. This is important, but you can switch off, and this is like have a very critical load. So even like if you think about your university, some of that lab where you need like 24 or 7 supply, that is like your critical load. Some of them like it's important, but still you can switch off. So for example, like you have got a like air conditioning or water heating that you need it, but still I mean you can turn off for a certain period. And some of them even like not that be important I mean during that in emergency period. So that you can completely disconnect it for that particular period. So that's how I mean you can um, categorize the load. And this is just showing one example of electricity network model. So as I mentioned, like, you need a single line diagram. And then if you do like, initial very simple load flow study, that will give you, all the, voltage magnitude, power flow. And from that also like capacity for different devices. And that from that, how you'll see that, it is actually satisfying all the requirement from that grid operator. Is there any questions so far? What we have discussed regarding the microgrid design? No question or comments?
How accurate should be our design, sir?
Sorry?
How accurate should be our design, sir? I mean,
Well,
is there any some band of tolerance?
yeah, that's a good question. Again, that depends on how reliable your system you want.
Okay.
So if you want like your reliability and resilience index is very high, then definitely your design should be more accurate. But having said that, also while we do planning and designing, we also do some sensitivity analysis as well, right?
Okay.
So
Yeah.
in most of the cases, we see like if something happen, for example, let's say 5% changes in all the parameter, 10% changes in the parameter, and then how your system is behaving. So that will also give you like that even like if something happen with that 5% range, still your system will not have any negative uh, issue in your systems. So
Okay.
that's we always do after um, having that initial design. We also do sensitivity analysis.
Okay.
Next, I'll just show you like one microgrid that is in Griffith University, where actually I was involved in that microgrid project. So that microgrid project was funded by Queensland government, and there were 3 industry that was involved, and the total project was as a big money that was more than $5 million. So here what we did actually, we design and install a test microgrid in that particular campus. So we consider like 3 building, and then we use that 3 building in the microgrid. So initially we started with the 1 building. So here in the building we have 30 kVA STATCOM, which is nothing but a fax devices, and I already mentioned like this one function is to regulate the reactive power. We have got 10 kilowatt SMA inverter. Also we have got like DC to DC. Sorry, this is not inverter, but this is like a DC to DC converter. We also have some existing inverter, converter before we started that microgrid. And then on top of that, so that's the initial we designed, but later also we included battery, electric car charging system, and so on. And here also, different that board that you can see, like distribution board. So also we have got like that monitoring system, data connection point, AC and DC rail, and so on. so on. So this is just showing for like connection for a particular building. And this is just like, you know, photos for that devices that we have. So as I mentioned, like 30 kVA STATCOM, that is, you know, look like this one. This is that, you know, building inside control and communication station in that particular building we have. And it also have some monitoring system component, data logger, Raspberry Pi, and so on, just to, you know, collect the data and do some analysis. As it also have 60 kilowatt hour battery energy system from Toshiba. And then it also have that, you know, DC to DC converter that I already mentioned. That one just showing like overall energy conversion in that particular solar system, that we used to get like 20% energy efficiency, but that was quite latest solar panel that we use. And also, like, you know, the SMA inverter, that is also quite good inverter as well. And then the charging system that we have, the efficiency was 95 to 97%. And considering that, you know, battery efficiency like 97%. And finally, I mean, here with charging and this, we used to get like efficiency like for the storage around like, you know, 92%. It's not including battery, but just for charging and then the battery charger and the battery. And then this is just like, you know, real microgrid signal that, I mean, you can see from that particular microgrid. The first one is just showing real power. I mean, that's a solar input power, DC to DC, like, you know, converter output power. And then it shows like DC bus voltage. So the middle one showing that, I mean, voltage, and the bottom one, it is also showing like, I mean, different phase demand in terms of like the current, and also like the DC voltage response as well. So that's like the microgrids that's, as I mentioned, like, you know, we have in the campus. So any question or comments so far?
Fine,
Okay,
sir.
there is no question or comment. I'll just give you 5 minutes break, and then I'll start after 5 minutes.
Sir?
Yes, Vijay.
Sir, I just have one question about this campus microgrid you are showing right now.
Mm-hmm.
Sir, is it capable of preventing GICs from entering it?
So GIC means, are you talking about induced current or?
Yeah.
So honestly speaking, I mean, we did not measure that current. I mean, when I was there,
Okay.
but I think that one is still operating. But I believe that, because it was also checked by like real, like, a body. I mean,
Okay.
before giving us the green signal that everything is okay,
Okay.
like the electrician and so on. And I believe, definitely they have checked that one, because if that value is high, definitely they will never give you, permission to operate your own microgrid. So I
Okay.
don't have
So
that,
by default, people are actually
yes.
joining it with the design. I'm not sure because uh, I mean researches are being conducted every year for decades for on geomagnetic induced currents, but uh, I don't think it's given the respect it requires in a practical scenario.
Yeah, that's you are, completely right, because when you see like mainly in our area, you will get 100,000 of papers.
Yeah,
But when you are looking for like something you really practical, you know, product that you want to implement, sometimes it's very difficult to find that,
yeah, exactly.
because the, in power system mainly, we did not think about enough for our research translation, like converting your research into a product.
Yeah,
And in recent year, most of that, um, university industry, even in Australia now, like publishing paper, they don't care, how many paper you publish, like as an academic, like for myself as well. They'll think about, like, what impact you can make it on your community, on your business. And to do that, I mean, always we need to think about how we can, um, you know, convert our idea into a real product that would be useful for, community business. Because if there is a no use, uh,
there's
um,
no point in even working
there
on
is no point, just like, for the sake of,
it.
publishing, you're just publishing something, right?
Yeah,
Um, Although, I mean, I'm not saying that, we don't need theoretical research. Definitely, I mean, we need theoretical research. But those people, I mean, we are more in the application side. We are not developing any new theory.
okay.
Then for us, I mean, probably, we need to think about more about uh, in the practical application side. Because many of us, if you think about like the control, there is a dedicated people, control engineering people, they are developing
Yeah,
new control theory, right?
yeah,
But for us, we are just utilizing their, in most of the cases, we are utilizing their theory,
yeah,
right?
exactly, exactly.
And even think about the optimization. For us, like, who is working in the power system side, probably we are just utilizing the existing algorithm, but I mean, existing theory. Sometimes for our just application, we are just making, minor modification.
Did.
So same thing like here. That's why I completely agree with you that this is the time. We need to think about the impact, not about the number, like how many conference, how many journal you have published. But I think even if you publish one journal and if you can convert that into a product, that would be like more effective than publishing 100 papers and
Of course.
none of them is practically implementing
Patentable.
in
Yeah.
anywhere.
It's true, sir.
Yeah. Anyway, next let's start again. Sorry, something happened. Just a minute. So, hi Aldab, can you hear me?
You're audible, sir.
Yes, sir, you are audible.
Okay, so your next event will start at 8:30, right?
Yes,
So in between I need like probably 10 minutes. So I'll finish
yes,
at 8:20 today, and then I'll
yes.
join 8:30 again.
8:30 again. Okay, sir.
Yeah, just sorry. It's just having some issue with that WebEx. Um, Sorry, I mean, can you see my screen now?
Yes, sir.
Thank you. So other than that microgrid, I mean, we also, I mean, developed a mobile power station with one of the local power electronics industry in Queensland. So here, I mean, you can see just like a box. So this one has got just like, connection point, and it has got internal, I mean, all the control converter, inverter that we need. So this one capacity was 5 kilowatt. With like 4.8 kilowatt to 40 volt inverter, 48 volt 200 ampere hour battery, and as I say, like this is like 19-inch rack cabinet. So this one, I mean, we designed with them, and also, I mean, we did all the testing, I mean, in our lab, considering different types of load that we use, for example, heating, refrigerator, and other loads that we have got in the university campus, just to make sure that, I mean, it can continue to supply power in different operating condition. And that's one actually we sell few, I mean, in Papua New Guinea. So here, close to Australia, there are some small country still in some places they don't have any electricity. So this was just funded by a Australian, I mean, one company, and that was designed here, tested, and then that was installed. So this is also something like a country which does not have any electricity in the remote area. You could have some just like solar panel and battery there, and then this is a very simple device. You just took it there, put it there. It's not difficult to install it, just like a plug and play. And here we just like do some studies, and we just find like voltage, current, considering like different load. It is just some parameters that we, for example, it was maintaining like one of them important parameters, power factor, that was 0.98. This is very close to 1 per unit. And the frequency also like 50 hertz. And that was the battery temperature that was maintaining 33. So what I'm saying, like, and also voltage, you can see like close to 240 volt. So all the constant, I mean, it was satisfied by this mobile power station. Then some of the control that we mentioned, we also implemented that 3 microgrid buildings that I mentioned, like this is N44, N0. This is just the name of these 3 buildings. And as I said, like, it have got battery with energy storage system, and then that is N44, N05. It has got EV and plug-in hybrid vehicle charging station that can facilitate vehicle to grid operation. And then the another building, it has got very some sensitive load because that's a laboratory, so it needs like an uninterruptible power supply. So that's microgrid. As I said, like it has got data sensor based like a smart power meter, and this is the number, I mean, as installed in each of the building just to monitor and collect data. And this is the software, OSIPI software, that we used to collect the, I mean, data from all the sensor. And for monitoring control, it used like the Modbus communication protocol. Yeah, and here we have microgate central controller for that particular system. So that electric vehicle charger hub that has got vehicle to microgate capability. And while you have a vehicle to microgate, it could have a number of advantages. And here it's mentioned all the advantages that it can provide. For example, active power regulation, reactive power support, load balancing, load shifting, track of renewable energy sources, peak load shaving, and so on. And this is some of that single and three-phase charging rating, and how long it's using for charging, corresponding power, voltage, and the time that is needed fully charge that battery. And here is mentioned some of the challenges while you have got that vehicle to microgate, because it is a stochastic charging pattern, storage life cycle degradation, fast charging. It might have some impact on the battery, coordination of the charging, voltage fluctuation, harmonic distortion, peak demand management, and also finding optimal resources that you need for that microgrid. This one again shows the same thing, but in details what you could have in your vehicle to microgrid system. So this is the three buildings that I mentioned here, like building N44, where we have got a PV with a DC to DC converter, and then you have got a battery with a DC to DC converter, and it has got a DC load, and then it is connected with the AC bus through a inverter. Then another building, it has got some battery charging system with some load, and the other building as mentioned it's have some critical load in that particular building. And as I mentioned, that has got microgrid centralized control. So that's diagram for the overall control system. And as you can see that for all the devices, they have got local control, like all the converter, inverter, they have got local control. But at the end, it is connected with the centralized control, because the centralized control is collecting information from all of them, and then also it is sending back that command for all the local controller to follow that particular command to make sure that the overall microgrid operation is stable. And again, this is some of the console we use for inverter, converter, and AC, single phase, three phase charging system. So this is that interlinking converter for which connect your DC bus as well as your AC bus. And these are the control we use. Again, I'm not going to spend so much time here, but here, so initially you have got some reference signal. Then here we use so sorry, I should start from here. So this is the original system. We are measuring voltage. Then we have got power controller. From that power controller, we are getting reference voltage for the inner. So here initially you have got power controller. Then we have got voltage controller. Then we have got current controller, which is finally producing signal for your PWM inverter. So this is more just from that measure signal, you are just producing reference for from power controller, it's producing voltage signal for the voltage controller, and then voltage controller producing current signal for the current controller. And finally, I mean, you are applying a control to your modulator. So this is DC to DC converter control, because here we would like to control DC voltage where you have got like, reference DC voltage. So from that we calculate a reference current and comparing with the battery current, and then I mean you are controlling your PWM just to make sure that it also provide a rate of charging for the battery as well. So this is EV charger that is for fast DC charging system. So again, this is more like quite similar to your DC to DC converter, but only I mean the value for a DC signal, I mean here fast charging would be different because its rate of charging much higher than that, normal battery. So this is three-phase AC chargers. This is just like the configuration, and this is the real control. So you have got here like a three-phase inverter, and this is how I mean you measure like three-phase voltage current, and then again through this power voltage current controller you're finding reference signal that you are applying to your voltage source converter. And this is for like your single phase AC charger. Again, I mean, this is slightly bit different how we can convert from your single phase to like DQ model, DQ prime, frame, or three phase to DQ frame, just like different sort of equation. But at the end, I mean, the control, method is, all the step that we'll be following is quite similar. And then for electric vehicle also, I mean, we use some like constant. For example, what are the like maximum, minimum constant, and also like their EV owner preference, and also like what sort of EV capacity they will allow for this V2G operation. And then this one is just showing that overall control diagram for that microgrid. So here we have got like three layer of control. So the first layer, it actually controls that DC bus. So what it does, it check that whether it's maintaining that DC voltage requirement, considering what's the minimum value, what's the maximum value, and then if it does not satisfy that range, what it does, it says like whether like all the DC EV charging system, whether they have got any additional power that we can utilize, just to make sure that it actually regulate that DC voltage. If not, then what we do, we transfer power from that neighboring AC microgrid to that from AC bus to DC bus. And then and if they have got additional power, they will again see whether if other buses needed that power, then it will transfer that power. But the second layer is mainly responsible to control the frequency, and third layer it's responsible to control that AC voltage. And that's how we coordinated that control for all the buses, and then we applied that one using some real data from that microgrid. So for example, that real power output, that is real radiation, and also considering the real active and reactive power demands, which didn't consider like constant load. We consider the actual consumption, and then we compared it with uncoordinated charging and with coordinated charging. So the left hand side you can see like uncoordinated one. Sorry, here, it shows like in cases like the first one, it is voltage, this is frequency. Sorry, this is AC voltage, this is DC voltage, this is frequency. And it actually compares with, different option, like with only three-phase EV, with only single-phase EV, with DC EV. And here, this one shows like, maximum and minimum boundary. And here you can see that with only DC, I mean, it's not possible. So if you just like, with single devices, sometime, I mean, you cannot maintain that, requirement. And then, I mean, with that coordinated one that we mentioned, in all cases, I mean, so the voltage, DC voltage as well as AC voltage, it maintains that, maximum, minimum limit. Same for frequency, same for the synchronization as well. So as I mentioned like that, the synchronization is a quite problem, but here you can see that, it was isolated, then again connected, and you can see that it's quite synchronized, like with voltage, frequency quite well. So when I mean, it's got disconnected, and even if it is connected, still it provides like a synchronized operation. So here, I mean, another application also we did, that's peak demand management. And here we considered three different devices. One is photovoltaic PV, EV, and battery energy storage system. And also we consider real weather, load condition, and also devices dynamics as well. And we checked with, I mean, two systems, one from USA and another from actually Australia. And while we, I mean, did that, these are the some of the things, I mean, we highlighted in that particular application. So here we have got like a decision tree based algorithm that we developed. We also have like, coordinate control approach, so that, one devices can talk with other devices and then can, take that final decision. And then we also compare with artificial based method just to make sure that, whatever we are producing, that actually makes sense. So just for the validation purpose. And here we actually use two battery. One is Nissan Leaf, another was Tesla, and you can see that both have got their different capacity. And we actually make a relation between that mileage and SOC level. And we know that what are the like, average mileage they drive. So we make sure that the mileage they drive, that corresponding SOC, is maintain that minimum SOC so that it does not interfere with their daily requirement. And here that's the control that's I mentioned, like here with all the devices we have. And also we mathematically, I mean, develop the model for EV battery as well as PV. And also we have all the constraint that we like make sure that it's satisfied when we develop that algorithm. And again, this is like that decision tree based algorithm. I'm not going just read line by line because it will take time. But it's just based on like the different requirement, and based on that, actually, it's finally get that finally decided that which one should charge, which one should discharge, what time, for what duration, and so on. And then I mean we first we did the simulation, and initially you can see that the red one, that was that peak demand. But after that, using like two batteries, as I mentioned, like Leap and Tesla, you can see that when I've got higher capacity, even it can reduce the demand even further. That's blue and green, that shows like with two different capacity of this building. And then, I mean, we compare with, I mean, one existing artificial intelligence method. So although, I mean, it does not provide better performance than artificial intelligence, but actually it follows that trend with NN. And then we also validate that in the laboratory as well. It's not only simulation, but using a smaller capacity, PV battery, and also that, LabVIEW software with some deck we have in that lab, and then using that one we validate in the laboratory. So we just did make sure that what we did simulation practically, I mean, it can be, I mean, implemented as well. Now that's some of the application, but for microgrid who will design, there is IEEE standard 1547 series that you can follow for, like, so that for different rating, I mean, if there's something happen abnormally, what the time you will get, I mean, to make sure that you clear that even within that, and also for not only voltage but also frequency level as well. And also it has got some standard for for communication purpose as well. Now next one, I mean, it's not only microgrid designing and operation, but also that's in interconnection with the main grid. And that interconnection can be done in three different ways. One is just simple mechanical switch. Other could be, through some switch gear, or even like through power electronic interface. Through, I mean, just the normal circuit breaker. It's relatively, simple and inexpensive. But the speed of the connection is slow. It's take like 3 to 6 cycle to achieve like a complete disconnection. And the power flow through the circuit breaker, you cannot control it. And also that's electrical characteristic on both sides of the circuit breaker must be same. So there is no like, electrically, it's not like electrically isolated. The power electronic interface, it is a costlier option, but it is the most flexible one. You can control like both active and reactive power flow. Reconnection time would be faster than in the normal switch. So these are like some of that advantages. Only disadvantage is just like that cost. But you might know that, I mean, this is one of that future device. And this is like a very smart device. You might heard about like this solid state transformer. So many universities, they are like doing research on that one. So still, I mean, not commercially viable option in the market now, but hopefully that might come in the coming years. So it's not only like a normal transformer where you have got only like step up or step down based on that primary secondary number of turns, but on top of that, here you have got AC to DC inverter converter on both sides, and which can actually provide like the STATCOM function that I mentioned. So it can provide like voltage, reactive power, power quality control. So it will not only stepping up or stepping down. So this device also could be used just like interconnecting your microgrid to the main grid. Then other like not only the microgrid, other also like important topics, that's distributed generation or distributed power system. That is also, I mean, another like important area. I mean, you could think about, I mean, if you would like to do your masters or PhD, or even like an academics, I mean, if you'd like to work in the distributed power system, that is also like a quite important area that you can think of. Like why distributed, I mean, that's I already mention like some of the advantages that you can get it from microgrid. You also get it from distributed power system. What distributed system is not like a microgrid, cannot run during that in isolated mode. There are some of the generation you could have in the distributed power system, and not only different generation, but also storage load, power electronics interface. So other important topics you can also heard about like that, smart grid. And for smart grid also, like, there are number of definition you will get in the literature. But here, just like, this is more like a whole grid that manages electricity demand in a sustainable, reliable, and economic manner, built on advanced infrastructure. And also it has got like very intelligent control, optimization integrated with that one in the system. So the future grid, that's probably, most of would like to want, that can be achieved through this smart grid. And again, this is just like the comparison between current grid and smart grid. And I'm not going to repeat because this is something probably, I already covered. That was the next generation grid would look like. And as I say, all of them will be getting here, focusing not only the generation, but also the customer generation, distribution, as well as transmission. So all of the things, you will be getting here. So this is more like a intelligence system. Yeah, some people call it, I know, smart grid, but many people also don't like the terminology smart grid. You can also tell like intelligent grid as well. And this is something like, you will expect in your smart grid structure. So as I mentioned that you will be having different like intelligent transmission substation, distribution substation intelligent. You will have like different consumer prosumer with like a smart home, not only smart home, but also like for your business as well as um, industrial like buildings as well. And not only that, you will also have like your demand response, different smart meter, and on top of that, it will have your IT, Internet of Things, whether you can use for your online monitoring and as well as control. But again, it's not like that. You can easily build your smart grid. There are definitely you need different like fundamental technology, and not only technology, also you need like government policy investment on that. And here is just mentioned some of the fundamental technology you need for having that smart grid. You also need like that's the smart meter, advanced monitoring metering system, AMI. You also need like phasor measurement unit, PMU, for your transmission system to become like smart. And as I said, like you also need like several fax devices, and STATCOM is one of them. You could also think about high voltage DC, as I mentioned, not only high voltage AC. These are some of the issues. We talked many times that you could have when you have got large scale renewable energy sources. And if you would like to work with renewable energy sources, these are some of the problem you can think about. That grid interconnection control, voltage frequency regulation, stabilization of power with large scale renewable, different inverter, converter, control design. You also need to think, work on system security, reliability, stability, fault right through. of different devices, power quality issues, system inertia, frequency regulation, congestion of the transmission grid, overall system security is not only the power system side, but also the cyber security side, and how also you can satisfy different grid code requirement that you have got for future grid with large scale renewable.
Trupti? Trupti?
Sorry,
Trupti? Meeting झाली का?
can you please
Come on, please.
mute yourself? And why you need that? That also, we have talked many times. That's mainly due to that intermittent nature of the renewables. You could also think about working in the energy storage side. For example, one of them could be that if you work in the material science, like designing a microgrid with better materials, which can probably increase the energy density. You could also work on that, sizing and estimating the better performance parameter, for example, SOC, state of health, and so on. You could also think about, managing battery while it is connected with the main grid. Even you can think about as internal like cell level, battery management system, and also like the energy management system while connected with the main grid. And battery has got, different functionality, not only, charging and discharging, but it can also provide different ancillary service as well as contribute during the peak demand period. And not only like only battery, but as I say, like it could have different storage devices. For example, like the hybrid system with supercapacitor, mechanical energy storage, for example, the flywheel energy storage. The other one, superconducting magnetic energy storage, although it has got some limitation in terms of maintaining the temperature. You could also have like pumped hydro storage. So the other one, also the new storage, that's compressed air energy storage. But as I said, like not only single of them, but it could have combination of them, which is hybrid. And one of them definitely makes sense, that's battery as supercapacitor, because this has got very high power density and this one has got very high energy density. So when you have got high power density, within a very short period of time, you can supply more power. So that will like in short term, but when you have got high energy density, for a longer period of time, you can provide more energy to the system. So if you have got a combination of that, it could satisfy the requirement for a short period as well as longer period. So that's why it makes sense to have that hybrid combination. And this is just like the comparison of different energy storage devices, like in terms of energy density, power density, charge discharge efficiency, self discharge, which is definitely we don't want that. But if it happens, that would be like a losses inside the battery. And then this total life cycle, and how long you can think of about their durability as well. And this is just nothing but just different battery, lead acid, nickel cadmium, nickel metal hydride with the lithium ion. And as expected, probably in most of the cases you expect better service from that one, but definitely it would be expensive than other option. And while you need like like within a very short period of time, you would like to control the ramp, and you would make like a predicted system, and also you want to do the frequency regulation. We need like wind farm. You also need embedded energy storage system. And this is like the supercapacitor that's I already mentioned, but this is just giving like more details about the supercapacitor. Yeah, so that's probably all I would like to share. But if you have got, any question and comments, feel free to.
Can you just elaborate a little bit on grid code requirements?
So the grid code requirements, because every country have got their own grid codes. So for example, India, they have got their own grid codes. In Australia also have got their own grid codes. So the grid codes is nothing but they are all the requirements that you need to satisfy while you are going to connect a, like, for example, like say, let's say like a generating system or even like the microgrid with their system. And here these grid codes actually contain all of this requirement. For example, there's voltage. For example, this is the maximum, this is minimum, the power quality, uh, this is the minimum, and then for frequency, and also if something happens in the system, how long you will be given to come back to that previous within that acceptable voltage, and otherwise it will disconnect it from the system. So all that requirement that you need to follow, that is actually called grid codes. And as I say, like IEEE, IC, they have got their own standard, and many country they follows either IC, IEEE, or they might have some their like own requirement that you need to follow.
Sir,
Thank you very much.
sir.
Yeah, please ask. Please ask.
Sorry, I just went like little bit fast because before joining that next one, I just need a few minutes.
Sir, yes. Good evening, sir.
Yeah.
Actually, that this too much penetration of renewables, how it will affect the uh, transmission system observability, and how it will affect the state estimation, all those. Can you, if you have any insight on that?
Definitely. When you have a large scale, probably people now thinking about like online monitoring, and but again, online monitoring, if you would like to make like 100% system visible, you need like so many smart metering or PMU. Maybe for PMU, transmission system, mainly the PMU. But other technique, as you mentioned, the state estimation, that might be a way that also, you could also get that like operating condition for a transmission line. But sometimes also you could have a combination of these two. But with large scale renewable, definitely we need better better visibility. Otherwise, you won't be able to maintain that system requirements in terms of reliability and resilience. Because when you have got renewable, as I mentioned, that it has got impact, and that is quite very fast. So if you have a very fast impact, then you need a better device for monitoring as well as for predicting. Because if you don't have, cannot capture within a very short period of time, it something can happen, and that can make your whole system unstable. Because the renewable generation system, that does not have the same control capability as like our current centralized coal or gas, or other power station that we have. So that's why still um although we in like simulation paper, although there are many things that already mentioned, but if you think about like the real experimental, still I think maybe with 10-20% people have got some demonstration result. And but still I don't think people still have got very good idea what will happen. We have got 50, 60, or even like 90, 100% scenario. And as you know that impact will be different from one system to another system. For example, the Australian power grid impact could be different from the Indian power grid impact, because they have got their own like I mean, local, operational, weather condition as well as in operating condition. So that's why, there is still more work need to be done.
Okay. Thank you, sir. And one more question is, uh, what is the smallest time step size which we can observe the nonlinear nonlinearity in the renewable power generation, sir?
Well,
At most smallest step time step.
again, so are you talking about like through online monitoring system?
Yes, sir. No, no, sir. No, I'm not talking about monitoring, but I am curious to know about that renewable generation. Normally, if we take very less time zone, uh, well, though it is a non-linear power delivery will be non-linear, it may seems to be linear. But I want to know that. What is the smallest time step, at most time step, at which we can see the nonlinear behavior of the renewable power delivery?
Well, normally, our standard practice previously was like, 30 minutes, and then we did like 15 minutes. But now, like with all those, like, smart meter, even you can capture like that system response, even like in the millisecond range.
Okay.
So, but again, that is not available like, for all the power system. But I think the technology is coming which can capture that, very fast response. But, having said that, still, we did not have that, demonstrated result through that large penetration. So that, result that so far we are having like, might be 15-20% maximum. That probably, still it can capture. But having said that, people are at the same time, trying to improve their modeling as well as those monitoring system. So by combining these two, probably, still we need to do further works to even get like, better accuracy for those, non-linearity that you mentioned. Yeah, so.
But it as from your point,
But if you want like from offline analysis,
okay, sir.
then I think even you need a very complex model, and also you need to model all that, internal power electronics nonlinearity, which still have not been done yet, because this is very, very complex. And even if you can do it, and if you want to simulate, it will take hour and hour to simulate your system. So that's why, all the model that you'll be getting, they consider, they neglect many of the nonlinearity in the system, which we should consider when we'll be having large scale renewable.
Thank you, sir.
Yeah, we'll close.
Thanks, Altaf. So I think we have got 5 minutes.
Thank you
I'll
very
see
much.
you in 5 minutes
Yes,
time.
yes, yes.
Thanks, everyone.
Yes,
Thanks
yes.
for your attention.
Thank you.
And hopefully you will also be attending in the next session. Thank you.
Yes, sir. Yeah, please join validated.
Thank you.
The main things has been
The link
also
has
mentioned.
been shared.